Welcome back. In this module, we will start discussing about properties of polymers, and we will begin with thermal, mechanical and viscoelastic properties. But before we go into the properties, we will briefly discuss polymer processing. Let us revisit the different life stages and transformation processes which we discussed earlier. We have discussed how to synthesize polymers in first few weeks, and then once the polymers were synthesized, we discussed in following weeks how we can characterize the polymers both in terms of their molecular weight and their chemical composition. Now, once we are ready with the polymers, then we have to take these polymers to the final product formation. So, in doing that, it is generally two steps are followed. Sometimes one step is enough to make a product. So, in first steps, these polymer samples, which are mostly in powder or pellets or in emulsion form, they are added with some additives, and a process called compounding is carried out, and we get intermediate products like resins, pellets, granules and flakes. Sometimes in this step itself we can produce final products which have very simple shape like sheets, films, pipes, etc. Once we are ready with this intermediate product, then these are taken for further processing. In this step, we can add additives and do a processing which is called designing, fabrication, finishing to get the final product. Now, in laboratory, we do not actually make final product, these are done in commercial lines. So, to basically estimate the product performance in laboratory, some specific samples are produced having a well defined geometry, and testing are done with those samples and this testing data are correlated to the final product performance. So, the entire steps or these steps which basically takes the polymers which are synthesized to the final product formation, these steps are collectively called polymer processing. Now, I want to also make a point in this slide that generally polymer producers or polymers manufacturers, they do not actually sell the final product. For example, company like Bayer which makes polycarbonate, they do not sell the final product of a DVD or CD or a car headlamp or so on. So, a company like Bayer, what they do, they synthesize polycarbonate and sometimes they sell the powder, or sometimes they add different types of additives to make different grades of polycarbonate and then sell in the market. And there are other companies which buy from Bayer and further process it to make the final product which goes into the final application. So, now I will move the polymer processing in brief. Polymers can be formed, cast, machined and jointed with relatively ease, and it requires little or very low amount of post processing or surface finish operation. Polymers melt or cure at relatively lower temperature compared to say metal or a ceramic, and as a result polymers require lower energy to process compared to those materials like metal. And polymers are used to make reinforced composites. Basically, the other reinforced ments are done by adding some other components in the polymer mixture, which are not very easy to do with materials like metals and ceramic. And generally polymer process starts with the raw materials, which are commonly polymer pellets or polymer powder. Now, before we go into the polymer processing steps, we just revisit the polymer families, because the type of processing which need to be followed or the condition which need to be followed during processes depends on the type of polymers that need to be processed. And generally we have two types of polymers, as we discussed earlier: thermoplastics, which can be reformed after melting, and thermosets, which we cannot reform. Thermoplastics can be either semi-crystalline or amorphous, and thermosets can be elastomer or glassy. These are some of the examples of semi-crystalline and amorphous polymers, and these are some of the examples of thermosets polymers. Looking at the polymer, we need to basically determine the condition of polymer processing or the type of polymer processing we need to carry, with the knowledge that what type of polymer this particular which somebody has chosen to process is. Thermoplastics are two types, as we said: amorphous or a semi-crystalline polymer which contain both crystalline and amorphous region. Amorphous polymers are characterized by a temperature called glass transition temperature, and semi-crystalline materials are characterized by two temperature melting point which are related to this crystalline domain, and Tg glass transition temperatures which are related to this amorphous domains. So, we need to have a understanding of the values of these Tm and Tg to set the processing temperature. These are cross-linked material, thermoplastics, and 90% of the polymer markets are thermoplastic or consist of thermoplastics material. The other materials, as I said, is thermosets, which are cross-linked, and this is a mistake, 10% of the market is this is 10% of the market is made up of thermosets. And thermosets could be two types. If the polymer change, if the temperature of applications is below the glass transition temperature or Tg of the polymers, then this will behave as glassy, which is very difficult to process. If the temperature is above the glass transition temperature or Tg of this polymer chains, then these chains are flexible. So, you can stretch it, and we call this elastomer. So, hence if you want to process thermoset, the temperature need to be higher than the Tg of the consisting material. So, as I said that most of the polymers are made up of thermoplastics, about 90%. We will mainly discuss processing of thermoplastics in this lecture, and this line thickness will basically represents the extent of or the weightage of these processes. For example, most of the thermoplastics are melt process, and melt process are mainly consist of two steps. One is extrusion followed by a molding. Sometimes we can directly do molding from melt state. Some of the products are formed from the extrusion step itself, but most of the products are prepared or manufactured after in the molding step. A part of or a minor part of the processing is done in solution, that means the process polymers are dissolved in solution and then cast it to make products like film, or it is spun to make products like fiber. Sometimes this spinning can be done with the molten polymer as well, but the extent or the weightage of that process is much lower. So, we will mainly discuss the extrusion process and various types of molding process, because those are the most important or most abundant polymer processing steps done for synthesizing polymers product. This is the basically what is the extent different products are formed. Like most of the products are formed either by extrusion or by injection molding. Some products are formed using a process called blow molding, and there are other molding process which responsible for the other type of product formation. So, we will talk mostly about few of these important processes like extrusion, injection molding, blow molding and so on. So, in processing of thermoplastics, first step is we basically mix the polymer and then add different types of additives. We can regrind or we can make a master batch of additives and add this here, and we basically mix it in this step, and then we take it to next step. Basically, we melt it and do a step called extrusion. And as I said that from this extrusion step itself we can make some simple products like pipe and sheets, but in most cases these extruded products are followed by a second step, molding step, to make most of the products, and in this step, in this molding step we add other components like fillers, reinforcement agents, foaming agents, and we do this molding process, which could be different types of molding, injection molding which are used for common products, blow moldings, thermoforming, compression molding, and we can do other processes like fiber spinning, film casting, blown film for grocery bags, like that. This is a general rule is followed, that for amorphous material the processing temperature is typically between Tg plus 80 to Tg plus 140 degree. So, if the polystyrene is having a glass transition temperature of 100 degree centigrade, then polystyrene is generally processed between 180 to 240 degree centigrade. A polycarbonate which has a glass transition temperature of 150 degree centigrade, it is generally processed at say 250 or 270 degree centigrade. Similarly, for a semi-crystalline material, the processing done is above the melting point, 20 to 50 degree centigrade above the melting point. If the temperature is taken too high, then obviously viscosity will be too low, it will be difficult to process. Similarly, if the temperature is too low, then the viscosity will be very high, then it will be also difficult to process. So, this is a typical window of temperature in which or at which the polymer processing is done. So, in the extrusion process, this is a cartoon of a extrusion machine. There are screw inside, sometimes it is single screw or it could be a 2 screw, we call twin screw extruder, and this is a orifice which we call as a die. So, from here the product is basically taken out, and the shape of the die will determine what shape of the material or processed extruded polymers which are coming out. You can have a sheet type shape, so where you can, or a pipe type like circular die where you can directly get extruded pipes or sheets, or otherwise you can have a small orifice by which you can get a long polymer strands, and you can chop it, cool it and chop it to get small granules. So, in this case there are 4 regions. This is a feed region, this is the plasticization region, and this is the metering region, and this is die region. So, I am not going in details what is the role of each region, because that is out of scope of this course, but in this case the temperature is slowly increased from left hand side to right hand side, and the polymer samples are melted here and pushed by this screw and through these dies. This is the most common manufacturing for plastic resin, as I discussed earlier, combines pigment, additive and resin. It is a high heat process and high pressure process, molten mixture. In this process the extruded products are pushed through the die, and you can use different shapes of the die as well, and it creates warm plastics for further finishing operations like pelletizing, calendering or molding, as we discussed earlier. So, it basically gives the materials for further processing, the second step which we discussed earlier. So, it basically pumps the high viscosity melt, it also mix different ingredients. You can actually use this also as a reactor if we use the materials which reacts with each other, which is not very frequently done, but we can do that. We can use this extruder as a reactor also, and it can be used as a scrubber as well. So, it is a steady state process, high productivity, lower complexity of the parts which we can generate, low tooling cost and wide tolerances. So, that is the reason it is a very popular or very the most common manufacturing process for plastics resin. And as I said, that products with long uniform solid or hollow complex cross section like sheets, pipes etc., can be prepared by this extrusion process itself. Next we move to injection molding. Here this pellets or granules or powders are fed into a heated cylinder, and then using a injection mechanism, this melt is injected to a cavity which is having a particular shape depending upon the final product shape what we require, and this is done with the help of a screw. And once this molten polymer is injected into the cavity, it is cooled so that the shape is frozen, and then it is taken out from this cavity and we get the product. In this case, a dog bone shape sample is produced here, which are typical used for mechanical testing, which we will discuss later. So, in this case, products of complex shapes of different sizes can be produced, high productivity rate, costly tooling. This is most costlier than the extruded machine, and it has very good dimensional accuracy. Next, we will talk about extrusion blow molding. In this case, like the hollow products are generally PPS like this water bottle, water storage bottle, and in this case what is done, a paration which is a tubular profile which is extruded using a extruder, and then it is placed in a cavity where it is inflated using a inert gas, and once the inflation is complete, like it basically covers the entire shape of the mold which we are using here, like a bottle shape here, and it is cooled, and then once the cooling is done complete, the shape is frozen, then we can take out by removing these molds and cutting it from here, which is called ejection process. So, in this case this type of products are produced. So, this can be a continuous process. Hollow thin wall parts of various sizes can be synthesized, produced in these extrusion blow molding processes, high productivity rate and low cost for making containers. We can also have others type of molding processes which I will quickly go through, like injection blow molding in case short tubular piece or paration, as we discussed earlier for extrusion blow molding, they are injection molded and transferred to a blow molding die, and the rest of the process followed exactly what I discussed in last slide. Plastic beverage bottles or hollow containers are generally produced using this mechanism of process or this processing step. Multilinear blow molding, we discussed blow molding, and in this case the polymer which are used, like the extrusion, in the extrusion we extrude two layers, we basically extrude two or more layer one after one, and then using the same process we can make multi-layer plastic product which are used for packaging material. Multi-layers are necessary to use for different purpose like barrier and hydrophobicity, oil repelling and so on. Rotational molding, in this case pre-measured quantity of powder sample is placed inside one mold and then rotated on two axes inside a heated furnace, and it has low equipment cost, longer process time, and products like trash can, boat hulls can be used by this type of molding. Some structural foam material which are just little modification of the injection molding process. In this case, during the injection process, inert gas is also basically added or injected along with the polymer melt. So, the polymer melt will now contain these inert gases in the molded product it produced. So, in this case basically we call, now we discuss, we are making a foam product where gas are dispersed within the polymer matrices. So, it is a variation of injection molding process, particularly for large structural parts. Parts consist of a large and closed cellular core, means that gas or this gas core surrounded by continuous solid skin of polymer. A much lower pressure operation than conventional injection molding system, which allows much larger part to be molded in this case compared to a conventional injection molding process. Next we will talk about thermoforming. As the name suggests, we basically in this case we have a shape which is the shape of the product which we are planning to produce. These are used for products like tray and different packaging materials. So, in this case a film, polymer film is heated so that it becomes soft. So, it just heated above the Tg or just above the Tm of the polymer, mostly Tg, and then vacuum is applied so that now this film will basically form a shape of this mold, and once it is cooled, this film will form a product like a tray, as in this case it is shown here. So, the plastic sheets, this is a sheet is heated to a sag point, like softened but not melted, and this heated sheets placed over a room temperature mold, this is room temperature mold, and forced against vacuum pressure. So, basically vacuum is applied, so it is forced onto this room temperature mold, and once it is cooled, then it will form a product of this particular shape. So, appliances, housing, packaging, advertising, signing, refrigerator liners, these are the materials which are produced using this thermoforming process. It is shallow or relatively deep cavities can be formed, low tooling cost, medium protection rate. Next, we will talk about the processing of thermoset polymers briefly, and most common process is compression molding. In this case, the polymer or a pre-polymer, just before curing, it is placed into a cavity and then it is heated to a molten temperature, and because it has a curing agent, so it might start cross linking, and once it becomes soft, a mold is compressed onto this molten polymer, and then it is allowed to cool. Hence, this product will form the shape of the mold as is shown here, and once it is cooled, then you can take it out by ejecting process. Another process we can do is reaction injection molding. This is used for chemical reaction between two polymer material. Rubbers are generally processed by calendering, processing step called calendering. In this case, this is a process that produces for producing long run of uniform thickness sheets of rubber, either unsupported or on a fabric backing. So, a standard 3 or 4 roll calendar with linear speed range of 2 to 10 feet per minute is typically used for silicon rubber. Now, in case of polymer processing, as you now know that most cases the processing is done in molten state, and polymers are very high viscous material. So, in molten state the viscosity will be very high. So, injecting the material or using material or basically pushing the material through a mold or through a die, it will be very difficult because of the high viscosity. But fortunately, polymers are materials which are shear thinning, which means that at a high strain rate, the viscosity of the polymer melt actually decreases a lot. So, if we strain, like in the process when we are injecting the material, the polymer melt through a die or through using a screw, the shear rate or the strain rate will be much higher. As a result, the viscosity will decrease drastically, and this actually enable a polymer engineer to process the polymers in a cost effective way. Otherwise, it will be difficult for a polymer engineer to make polymer product in a cost effective way. Typical strain rate for different processes which I discussed are compression molding is about 1 to 10 per second, calendaring 10 to 10 to the power minus 10 to the power 2 per second, extrusion is 10 to the power 200 to 1000 second inverse. Injection molding is the highest having most high strain rate like 1000 to 10,000 second inverse. So, we now know how to make different type of products from a polymer which has been synthesized by different processes. Now, to basically estimate or determine the polymer performance, we need to test these products. Now, we cannot test in a laboratory, we cannot test the actual product. Hence, usually a standard samples or miniature samples are produced in polymer lab, molded samples are produced polymer lab, and different testings are done. The data from this testing can be used to correlate the performance, actual performance of the final products in most cases. So, in next lecture onwards, we will start understanding different properties of polymer.